So this is from problem 4.2.33, and what I've got up here is actually where part A already has some markings in there. So when part A asks us to find the starting points, what I look for is on our first two graphs here and here, what is the height at time 0? So where do they cross the y-axis? So here's one point, and then there's the other one. So this tells you your x graph at time 0 is at around -10, right? So x of 0 is approximately -10. And then it looks a lot like x dot at time 0 is pretty much 0. And so that tells me on my graph, where does the time begin? Well, on my x-axis, it must be at about -10, and my x dot on my y-axis must be at about 0. So that's this point right here. So that's where it begins. That's at time 0. So if I sort of start this, here's my initial condition. That's where we go. And we want to add arrows for the directions of each trajectory. And sort of write down these initial conditions. Okay. So here are our initial conditions, right? X. I just wrote those down. I'm reading for you part A. And for these trajectories, we're going to go from here. We're going to go along this way as time increases. Now for part B, it asks us to write the explicit solutions for x and x dot and use your initial conditions to solve the initial value problem. So I should have written the problem here. So this is x double dot plus 5x dot plus 6x equals 0. So if you're starting more or less from scratch here, you can take this and recognize that you have the characteristic equation. I could factor that. So it's a 3 and a 2. So that tells me my explicit solution here for my x value involves a -2 and a -3 in the exponent. So you can say x of time t is some arbitrary constant e to the -2t plus some arbitrary constant e to the -3t. It will also be incumbent upon us to take a derivative to give us -2 out in front and a -3 out in front like so. These are C that looks a little bit like an R, but this is in fact a C. C is shining C. Okay, so here are two functions. So in part B, we're still asked to use these initial values to solve these, and so let me just scroll down for a tad. So this first initial value says to plug in a 0 to x. So x of 0 gives you C1 plus C2, that equal to -10. My goodness, that was strange. That equals to -10. And then plugging a 0 into this one says -2 C1 plus or -3 C2 needs to equal 0. And this is then a way of solving it. So notice I just have to solve these two equations at once. You can notice then that this will actually give me, if I add it down twice, I'd have what -C2 is equal to -20, so C2 is equal to 20. Oops, that was way too large. C2, oh my goodness, I apologize about that. Okay, C2 is equal to 20, and if C2 is equal to 20, then C1 is equal -30. Alright, great. So here are our values. We use this to solve the initial value problem. So we could, if we wanted to, sort of finish out and say, that tells me my x of t is in fact negative 30 e to the negative 2t plus 20 e to the negative 3t, etc. All right, coming back up, we need to look at this because in part C, it asks us to describe how the graph for solutions relates to the explicit formula. So looking at this first graph here, let me actually, maybe we'll just bring it down with us. All right, so this first graph right here, white's a terrible color for this, well, that's how it relates to this expression. So what you might notice, these are a couple of things. You might say, well, we see when time equals 0, it follows that, but maybe beginning from time equals 0, if time, so this is for part C here, if time increases, what the heck, sorry, my keypad is being very strange. Right, as time gets bigger, we see in my graph that we're going to approach 0, right? And so thinking about this particular expression, as time gets very, very big, both these terms are sort of going to 0, right? But notice this term is a bit slower because there's that 2t as opposed to 3t. So that tells you that it will always be negative. So this term right here is always going to be the more powerful one as time increases. So that does make sense. So that's why in our picture, as it goes to the right, we are staying beneath that t-axis. That makes sense. And so, stays negative, and we should say that. As t, if you were to decrease, you would notice what should happen is there should be a point where these are 0, and then the positive one should be sort of taking over. And that also makes sense. So as time is sort of negative, you can imagine how both of these terms are increasing as time decreases, right? Since we would be then having a positive exponent. And the one on the right here is the more powerful one eventually. So there's a time where the one on the left is more powerful because it has that negative 30. But as time keeps going, its exponent is all that really matters. So that one would be the more powerful one, which tells me then as t decreases, it becomes positive, increasing. And you can also say that there's a certain point where they are equal, right? You can sort of balance them out, and you might wonder about that. So say, well, when does this happen? When are the powers balanced? And you can solve this. It's a little bit of algebra, but it basically just says 3 halves would have to be equal to what e to the, in this case, if I were to divide by, let me just write it out so I don't make a silly mistake here. So that would be e to the negative t. So you can solve that and say, I would, at the time, where it's the negative natural log of 3 halves, at that time, these powers would be equally matched. So you can stick that into a calculator. I have one here. So the natural log of 3 halves. So a negative version of that would be, this is approximately 0.405. So looking at the graph, that looks to be about right. So we don't seem to be all the way over to 1 or 2. So it's about negative 0.4-ish. So that makes sense for that first graph. Part D of this question asks us to compare the graph of x dot, of the first derivative of x with respect to time, to its explicit formula. So let me just do this. Let's make a copy of this. And we can drag it with us. So I'm just going to drag this down so we can talk about second picture here, and I will also have us recall. Let me actually just also grab our x dot formula. I guess I didn't actually write it down yet, so we can just write it. So negative 30 and 20. So from your x of t. All right, here we go. I paused the video for a second just to write down x dot, plugging in the constants that we found. So here's our explicit solution. And you could write it in a couple different ways. If it's easier, you could think about this as 60 times e to the negative 2t times 1 minus e to the negative t, if that's easier. Now what we need to compare is comparing this to its picture right here. So let me make it picture a little bit bigger. So the middle picture. And notice as time increases, it's always positive. This is part 2 of our problem. As t, my goodness, there was a lag there. As t increases, time is always positive, or x dot is always positive. And that makes sense here because when t is 0, this part right here is 0. But then as it increases, this internal part here is always positive, since this internal, or this e to the negative t, is going to be less than 1 for positive t's. So it's always positive. So that makes sense. That makes sense of why it happens. There's also seems to be a peak there, and so you can, if you chose, investigate when is this sort of at its highest. You can do that by taking, if you want a second derivative or a derivative of this and optimizing that. That's fine as well. That's a good thing to do. Maybe I'll do that in a minute. But I also want to just think about what happens as time goes in the other direction, right? If so, always positive. If t was going in the other direction, going to the negative, suddenly this part out here is always positive. Can't mess with that. This part in here, though, if t were going in the decreasing direction, this part in here would be negative. So that's why we always have negative values here, and it's negative, but everyone in the absolute value, these are increasing very, very quickly. So that's why it's sort of shooting down very, very quickly in the negative direction. So what I can do then is just say, basically write down what I just said. For the sake of this video, we only have a couple minutes left. You might ask about, well, where is that peak up there? So if I had to do that, let me zoom out just a tad. Oops, I guess I'm at the bottom of my slide. So what you could do to find that peak is to take a second derivative. So you say, well, x double dot is just negative 120 e to the negative 2t plus 180 e to the negative 3t, and then set it equal to 0. So likewise, you're going to get e to the negative t is